Hi everyone, welcome to the first lesson for topic 3.3 graph and networks. So personally, I think that this is one of the most interesting topics in our syllabus. So I hope that you are enjoying learning it as well. Okay, so let's look at the learning outcome of today. So we are going to learn the definition of a graph and the associated terminology. So you can see that there are like all the different terms that you will be introduced for today's lesson. But don't worry about that. I mean, it's quite a lot here, but eventually after you understand what is the meaning of each of the term, then you will be able to use it. Okay, so let me try to simplify the whole thing that we are going to learn today. So basically we are looking at two things. So the first one is what are the basic elements in a graph? Okay, so the first subtopic is what is the element in a graph. So the second one is we are going to look at the different types of the graph. Okay, so basically that's the two main things that we are looking at today. Alright, so let's start with the first subtopic. Okay, let's start with the definition. So the big idea that we are learning here is called as graph theory. Okay, so it involves like topic 3.3 graph and networks that we are learning right now, and also topic 4.3 in future, which will be dealing much on application and different algorithm. Okay, so graph theory involves the study of diagrams. So all these diagrams are called as graph and networks. So what is that meant by graph? So when you first heard of this word, you might be thinking that graph, is it like a bar chart, a line graph, or it's like histogram and so on. But in graph theory, the graph that we meant here is a diagram that consists of points, which is called as vertices. Okay, so in singular, it's called as vertex, all right? So that are connected by lines, and the lines are called as edges. Alright, so all this terminology is very important because when you try to explain something, when you try to describe something, you must make sure that you are using the right term. So for the points, right, we don't call it as points, we call it as vertices. For lines, we don't call it as line, but we call it as edges. So later you'll be looking at all this term in a much more visual way, and I hope that can help you to understand better. Okay, so a graph meaning the diagram, right? So when we try to use the graph in some application, so it is called as network. Okay, so network is the practical application of graph, and they are just a part of our life. Okay, so you can imagine like the routes that we are traveling on. So when you try to put them on a map, so you can thinking the pipes that you use to connect each of the house in like one city, that gives you like a network also, the electric cable, even, oops, I'm sorry for that. I will try to change it in the handout that I sent to you. This is a food web. Okay, so or even like a result of a sporting competition, they are all examples of networks. Okay, so a simple example that I put in here is like this is the map that you can see. So connecting the routes, connecting all the different towns in one of the region. So we can always try to represent this map by using a graph. So the graph will eventually become like this. So you have all these vertices connected by the edges. So the vertices here represent different towns, and then the edges here represent the routes. Okay, so you can see when we try to convert it to a graph, right, then the vertices in the graph are normally labeled by single letter. So in this case, then it's the first letter for each of the town. So this is like one of the simplest example that we can see here. Is just an idea for you to understand what is a network look like. Okay, so now we'll be looking at some basic elements in a graph that you should know before we move on. Alright, the diagram below illustrates the different components of a graph. So this is an example of a graph. So I hope that it explained the definition just now, that a graph is a diagram that consists of different points, which are known as the vertices, and then all these vertices are connected by lines, and the lines are called as edges. So whenever we talk about graph under this topic, right, you should be able to relate it to the graph under graph theory, but not the graph in statistics. Okay, so let's start with the basic elements that we have mentioned just now. So the first one is for all the points here is known as vertices. Okay, so you can see the all the italic words here is like the explanation for each term. So the points or the nodes here are called as vertices. Okay, so in graph theory, we don't call it as point, we call it as vertices. Then after that, all this line that connect all the vertices together is called as edge. Okay, so I'm referring to like this line, so edge. Or in this case, or I'll write plural, then this is the singular. So same thing, vertex, then you have, sorry, vertices, then the singular is vertex. All right, so meaning one point. Okay, so now we'll be looking at different situation for like the special vertices or the special edges. So let's start with the point E here. So you can see E is a vertex that is not connected to any other vertex in a graph. So it stands alone here and is not connected to any point here. So this kind of vertex is called as isolated vertex. So which means that it is not adjacent to any other vertex, it's not connected to other, so it's like isolated. Okay, so now let's try to look at these two. So this is like the special kind of edges that we have. So for this case, you have two vertices A and B, but then they are for A and B, the same pair of vertices, but then you have two or sometimes it can be more edges that connect the same pair. So in this case, what do we call these edges as? Is called as multiple edges. Okay, so which means that it's the same pair of vertices, but you have like two paths that you can go from A to B, like either you can go for this way or you can go from this way. So this is called as multiple edges, like same pair of vertices connected by two or more edges. Okay, then the last one here, you can see that these edges connects the vertex back to itself. So you can see the starting and the ending is like at the same vertices. So this kind of edge is called as loop. Okay, so you might need some time to actually, remember all these words, but after you get used to it, then you will be able to use it like quite naturally. So don't worry about that, but to understand every term I mentioned here. Okay, the last one that we want to talk about is phase. So I want you to try to label like this thing. So we are going to see. Okay. So what is that meant by phase? So the phase is the separated region in a graph. So for example, this is like one of the regions. So this is like consider one phase, two phase, three phase, and outside we also call it as one phase. Is it okay? So you can see all these regions are separated from the other. So each of these separated region is considered as one phase. So this is what is that meant by phase. Okay, so in this diagram, you can see how many vertices you have. 1, 2, 3, 4, 5, right? So isolated vertex is considered a vertices as well. So don't forget to count that. So in this case, we have 5 vertices. So how many edges we have? 1, 2, 3, 4, 5, 6. So loop is considered as 1. So that's why 6 edges. So how many faces? How many separated region we have? 1, 2, 3, 4. Remember, outside is counted as one face as well. So that's why 4 faces. Okay, so I hope that you have no problem with all this basic. All right, I hope that you are still okay so far. Yeah, so next, let's look at the next term. Okay, so we'll be looking at the term of what is that meant by degree of vertex, or this is the words that we use in syllabus, but sometimes in books you will see they use the word order of vertex. Okay, they means the same thing. So degree of vertex is the number of edges incident with the vertex. So the loops will be counted as twice in degree of vertex. So it is denoted as degree V. Okay, so let's try to see how to calculate that. So it's actually very simple, which means you only need to find out how many edges incident with the vertex. So for example, degree A. So this is our vertex A, right? So how many edges incident with this vertex? So 1, 2, 3, and 4. So degree of A is just 4. Okay, so degree of B, same thing. Let's try to look at B here. So multiple edges, right? So 1, 2. So that's why in this case, the degree of B is 2. Okay, so degree of C in this case. So don't forget, just now we said that loop is counted as twice. What is that? So because you can move from here to here and you can move from here to here as well. So that's why this is considered like 1, this is considered like as 2. So although they are on the same edges, right? But when we try to calculate the degree, they means 2. So 1, 2, 3, and 4. Okay. So in this case, the degree for C is 4. So degree for D, so this is simple. So 1, 2. So 2. And degree of E, since it's isolated, right? It is not adjacent to any of the point. It's not connected. So that's why it's just 0. Okay, so the last thing before we move on to the example, so is the idea of adjacent and connected. Okay, so I know that previously, if we try to talk about like in daily life, right, when we try to talk about connected, it actually meaning like A and D are connected to each other, D to C are connecting to each other. But in graph theory, right, connected meaning reachable. So which means that in this case, actually B is connected with D as well, although you need to pass through A. So as long as you can reach donkey from B, then it's considered as connected. But we need another term to represent that what is the one that is directed connected. So this is called as adjacent. So two vertices are adjacent, which means directly connected if they are joined by one edge only. Okay, so in this case, you can see that, for example, A and B are adjacent, A and C are adjacent, C and D are adjacent, A and D are adjacent. Okay, so whenever, the other thing is connected. So two vertices are considered as connected when there is a path exists from one vertex to another, even you need to pass through the other. Okay, so I hope that you can see the difference between these two words. For example, B and D are connected, but B and D are not adjacent because you need to pass through two edges for you to reach to D. Am I right? So for example, D to C is also connected but not adjacent because you can reach C by passing through A. So A and D, A and C, they are connected and also they are adjacent as well. So the only isolated vertex here, meaning they are disconnected from all the other vertices. So that's the idea of it. Okay, so now let's try to look at example 1. Alright, for each graph below, identify the number of vertices, edges, and faces. Okay, I guess it's pretty simple. So let's look at the diagram 1 here. So the first graph. So we have 1, 2, 3. So 3 vertices. It's just for you to understand all the idea here. You can just write V, E, and F lah. No need to write the whole thing. Okay, so how many edges here? 1, 2, 3. So 3 edges. So remember, this is known as the, what is this called already? Yeah, multiple edges. Okay, so how many face? 1, and then outside 2. So in this case, we have 2 faces. All right, so B, 1, 2, 3, 4, 5. So 5 vertices. So how many edges? 1, 2. So remember, yeah, in this case, although from this vertex to this vertex, it seems like 1 edges, but how do you consider as 1 or 2 is depending on the vertices that split it. So which means that if there is no vertices here, right, then this is counted as 1. But since there is vertices there, then which means that each of the line that connected the vertices are considered as 1 each. So in this term, then which means you have 1, 2, 3, 4, 5, and then 6. Okay, so 6 edges. So how many face? 1 outside and inside here. Okay, so 3 faces. Okay, and the last one, 1, 2, 3, 4. So don't forget, isolated vertex is considered as one of the vertices as well. So how many edges? 1, 2, 3. So 3 edges. So face, then you have inside and also outside. So 2 face. Okay, so let's move on to example 2. Okay, consider the graph below. Okay, so A, the question wants us to name the isolated vertex. So in this case, you can see the isolated vertex is here. So A, C. Okay, so B, which vertex is adjacent to A? So remember, adjacent meaning that it's connected by only one edge. So A is here, adjacent, so which is only vertex E. Okay, so the loop in the graph connects which vertex to itself. So you can see there's only one loop in this graph, so which is at B. So the answer for part C is B. Okay, the loop in the graph connects C back to itself. right? Connect the vertex B back to itself. So which pair of vertices is connected by multiple edges? So you can see is D and E. Okay, so D and E. All right, as simple as that. So let's move on. Example 3. All right, so this is the map that we have in the definition just now. So it's a map of Southwest Victoria. Okay, so the question is asking how many edges are adjacent to Hamilton. Okay, so in this case, then you can see H is here. All right, so how many H are adjacent? 1, 2, 3. Okay, so that's why 3H. So if you want to write further, then you can just write we have HW, we have HG, and also we have HB. Okay, so B, which town are adjacent to Melbourne? So Melbourne is M, so you can see it's here. So adjacent meaning that you can reach by using only one H. So that's why B and G. So in this case, you just write down the full name, okay, of the town. Okay, so C, which town are connected to Melbourne? So which means connected, you still remember? So although you need to pass through other points, but it's reachable. So which means every of these towns are considered connected to Melbourne. So that's why just copy down every of the name. So H, W, whoa, long. Okay, and then B and also G. Okay, so you can remember it like this. As long as the vertex are adjacent, right, they are confirmed connected as well. So adjacent is one part of connected, but if they are connected, it doesn't mean that they are adjacent. You get what I mean, right? So for example, the B and G. So these 2 points, so these 2 vertices are considered as adjacent and also connected. It's like directly connected. But for H and W, they are just connected, they are not adjacent. So that's the idea. Okay, D, which town is directly connected to every other? So which is the town that is adjacent to every other? So you can see there's only G, that you can reach to all the other town by using only one H. So which means is G. Okay. All right, E, which town is not directly connected to Ballarat? So B is here, so not directly connected, so which means only W. So that's why W. Okay, so this is like one of the simple application of graph that you can see. So you can always try out also the example in your textbook, then you can see all the other example. So these are like very simple application like is most likely like general knowledge like common sense. So in future when we talk about more on application, then you'll be learning like more algorithm for more complicated situation. Okay, so let's move on to the next part of the notes. All right, in this part, we are going to talk about different types of graph. So there will be a lot of new vocabulary as well. So just take your time to understand every one of it. Okay, so all graphs are made up of vertices and edges. Okay, so this is what we have discussed just now. So how do we categorize the graph into different type, right? Is based on the composition of the vertices and edges. So by looking at the graph itself, how is the arrangement of the vertices and edges, then we will be able to identify which type it is. Okay, so let's start with the basic type first. So the first one, so as you can see, this is a graph that has no loop and multiple edges. So this graph is called as a simple graph. Okay, so a simple graph contains no loop and no multiple edges. So you can see it's always like a straight line connect, like the straight edges connecting to all the points here. So which means in this case is like if I try to add on one more edge here, right, then this will become a multiple edges. So that's why this is no longer a single graph, a simple graph. So if let's say I try to add on one loop here, then this is not longer a simple graph as well. Okay, so a simple graph cannot have any loop or multiple edges. And all the simple graphs are not directed and not weighted. Okay, you'll be able to understand this term when we move on to the type of the graph when we discuss about directed graph and weighted graph. So I'll come back to this later, yeah, because I don't want to make you confused for now. So just remember that this is like one of the example of simple graph. So when you see there's no loop, no multiple edges, then it's called as a simple graph. Okay. So the second type of graph that we want to see is this type of graph, which is called as a connected graph. Okay, so what is a connected graph? So a connected graph is one type of simple graph as well. So which means that you cannot have any multiple edges or any loop. Okay, so a connected graph is a simple graph which contains no isolated vertices. So that's why it's called as connected. So connected meaning every vertex is connected, or in another words, in like our daily usage, then we'll say every vertex is reachable to any other vertices, right? Every other vertices. So that's the idea. So you can see that no matter which vertex you want to start from, you'll be able to reach to the other vertex. So all the vertices here, they are connected to each other. So that's why this is called as connected graph. So which in other words, there is a path between any two vertices of the graph. So if let's say you try to add one more point here, then this is isolated. So this point is disconnected from the other vertices, right? So that's why this graph is no longer called as a connected graph. So that's the idea. Sorry, I think I made a typo here. So yeah, when you receive your handout, you should be able to see that in your notes, right? I will try to remove this part. So yeah, please remember that for connected graph, it doesn't need to be a simple graph. So the main idea is to make sure that all the vertex are connected to each other vertex. Okay, so which mean that if let's say there's a loop here, or which mean there's a multiple edges here, so as long as all the edges, all the vertices are reachable from the other vertex, so this is still called as a connected graph. It doesn't need to be a simple graph. Okay, so some notes here is that there's some special element which is called as a bridge for connected graph. Okay, so you can see that whenever I try to put italic, it's not like another new type of graph. It's like the nodes further from the previous type. So this is like under connected graph. So what is that meant by a bridge? A bridge is an edge in a connected graph that if you remove it, then you will leave the graph disconnected. Okay, so let me try to give you an example by looking at this diagram. So now this graph is a connected graph. Everyone agree with me, right? So, although you can see that's like empty for A to B, but then eventually you can actually reach A passing through C, D, E, F as well. So that's why all these points, they are connected and they are reachable to every other vertex. So this is a connected graph. Okay, so now what is that meant by a bridge? So I'll try to use the white color so that I can try to do it like erase it, then you see it. Okay, for example, when I try to remove the edge from A to F, okay, so what you will see, is it still a connected graph? Yes, right? So there is no isolated vertex. So every vertex still connected to every other vertex. So that's why AF is not a bridge. Okay, so now what if I try to remove D and E? DE. So you see, everything is still connected. Am I right? So this is still a connected graph. So that's why ED is not a bridge as well. So now, what if I try to remove BC? So what do you realize? Now, you will actually make this graph to be disconnected. Why is that so? Because B is isolated now. B is disconnected from all the other vertices. So that's why in this case, BC is one of the bridge. Okay, I hope that you can get what I mean. So let's try to identify one more. So in this case, maybe we can try to remove CD. Okay, so you can see when I try to remove the edge for CD, what happened? So these two part of the graph, they are disconnected from each other. For example, you can't you can't reach B, F, E, or D from B or C. Am I right? And from A, F, E, D, you also can't reach B and C. So that's why there's no isolated vertex, but eventually your graph is not connected in this case. So that's why CD is considered as a bridge as well. So you can try out for the other, if I try to take out AD, then you see everything is still connected. So for this graph, there's only two bridges here. So which is the first one is what we mentioned, what we found just now, BC, and also CD. Okay, so the idea is as long as you remove the edge, then the graph will be disconnected. The graph is no longer a connected graph, so the edge is called as bridge. Okay, so let's move on to the next one. Okay, so the next one that we are going to look at is called as the complete graph. Okay, the idea of complete graph is a bit similar like connected graph that we mentioned just now, but then what you need is more rigid here. Okay, for connected graph, we talk about that for every vertex, it is connected to every other vertex, right? So there is no disconnected part in the graph. Okay, for complete graph, you need to have every vertex connected to every other vertex by only one edge, which if I try to put it in another words, which means that every vertex must be adjacent to every other vertex. So you can see for this example, if when I try to look at these vertices, you see all I have the edges that directly connected these vertices to other vertex. Is that okay? So the same thing, when you try to look at this, then it's like directly connected or is adjacent to all the other vertex that you can see in the graph itself. So no matter which vertex that you are checking on, so you should able to reach the other vertex by only one edge. So which means all of them are adjacent. Okay, so there's a formula that can help us to calculate if let's say you have how many if let's say you have a certain number of vertices in your graph, then you'll be able to know how many edges that you need so that it is a complete graph. So a complete graph with n vertices is known as Kn. So K means complete graph, n meaning how many vertices that you have. For example, in this case, this is a complete graph because you can see that all of the vertex, they are adjacent to each other. Am I right? So this complete graph is denoted as K4. Why is it 4? Because there are 4 vertices here. So that's why K4. For this complete graph, you have 5 vertices. So that's why it's K5. Okay, so how can we calculate how many edges for each of the picture here? So we can use a formula that tells us that for every complete graph with n vertices, it has a number of n minus 1 divided by 2 edges. Okay, so let's see how can we use it. So for example, this complete graph has 4 vertices, right? So that's why let's substitute the n as 4. So 4 and 4 minus 1 divided by 2. So we have 4 times 3, which is 12. 12 divided by 2, we get 6. So let's try to check with the graph that we have. So is it there is 6 edges here? So 1, 2, 3, and then 4, 5, and 6. So that's why it's correct. So a complete graph with 4 vertices will always have 6 edges. Okay, so that's the idea. You wouldn't have more than that or you wouldn't have lesser than that. So you imagine if let's say you have lesser than that, right? Which means, for example, if this one, you round it off, then you're left with only 5, then in this case, it's no longer a complete graph because these two vertices here, they are not adjacent to each other. You get what I mean, right? So in this case, you might be thinking like, can it be, if let's say I try to add one more edge here, yeah, so you must remember for complete graph, it must be a simple graph as well. So that's why if let's say you have like multiple edges or a loop, then it's not considered a simple graph anymore. So that's why a complete graph with 4 vertices will always have 6 edges. Okay, so let's look at K5. So if let's say it's K5, then which means that the number of edge will be equal to 5 times 5 minus 1 divided by 2. Okay, so 5 times 4 divided by 2, which is 20 divided by 2, we got 10. Okay, so same thing, let's try to see whether we can see that or not. So how many lines that we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So which proves that this is correct as well. Okay, so this is like the formula that you might need to remember for complete graph, like how many edges that you have. So that's why when you are given a certain number and you need to draw it, right, you wouldn't be left out any and you can always check it out. Okay, so let's move on for the next one. Okay, the next special type of graph that we'll be looking at is called as a bipartite graph. Okay, bipartite graph. So it is a graph where all the vertices can be split into two distinct groups. So as you can see for this example of graph here, right? So the vertices are grouped in group 1 and then group 2. So these three vertices are under group 1 and this one under group 2. So when you try to look at all the edges that connecting the vertices together, they connect one vertex from group 1 and another vertex in group 2. Am I right? So when you try to look at this edge, so group 1, group 2, group 1, group 2, group 1, group 2, group 1, group 2, group 1, group 2. So each edge only connects each vertex in the first group with the vertex in the second group. So which mean if we try to explain it in another words, which mean that there is no edge that will be joining the vertices from the same group. So which mean that you wouldn't be able to see something like this. If you see something like this, then which mean that the vertices cannot be split into two distinct group already, because now you have an edge that connecting the vertex in the same group by an edge. Am I right? So each pair of the adjacent vertices must involve only one vertex from one group and the other vertex must be from the other group. Okay, so that's the idea of bipartite. So when we talk about bipartite graph, right, that can be a complete bipartite graph as well. So as long as all the vertices in group 1, they should be adjacent to every other vertex in group 2. Because we know that for this graph to be called as bipartite graph, you cannot expect that you have lines here, you have edges here. You got me right? So that's the idea. So which means that when we say that the bipartite graph is complete, it actually means that every vertex of the first group is connected to every vertex in the second group. So it's the same thing. If the vertex are under the same group, they cannot connect to each other. So that's why by looking at this, so you can see 1, so 1, 2, 3 to the second group. So this one 1, 2, 3 to the second group. So this one 1, 2, 3 also. So this is like a complete bipartite graph. But of course, because this is a complete bipartite graph, it's not a simple complete graph that we mentioned just now. So you cannot use the formula Kn just now, yeah? So this is for bipartite. Okay, so how can we actually identify and see whether a graph is a bipartite or not? So we'll use a technique which called as vertex coloring. So how can we do that? So if you have highlighter, then you can prepare it. So it will be easier for you to, do it on your paper. So what do we need to do is we use two color to color all the vertices such that there is no same color vertices are connected by one edge. If you are able to do so, which means that this graph is a bipartite graph. Okay, so let's see. I try to use the first one is yellow color. Okay, so when I try to do, then I try to color A first. Okay, so the idea is I must make sure that there is no vertex that color with the same color that is connected by one edge. So which means that A and F is connected by one edge, so that's why I cannot color F as yellow. Am I right? So that's why E is not connected, so maybe yes. Okay, and then D is directly connected, so cannot also. Then for C, yeah, it's not adjacent to A, so that's why I can do this. Alright, then after that, I will use the other color and check whether it works or not. So for example, for B, so A to F, because it's on one edge, right? So that's why I should be using different color, which in this case, I use blue color. So A, F, so D is adjacent to A and D is adjacent to E. So I cannot use the same color, which is the yellow color, right? So that's why I'll use blue color. So the same thing, B is adjacent to C, so I'll use blue color. So as long as you'll be able to color all the vertex by there is no same color vertices connected by one edge, then this graph is a bipartite. If it's not a bipartite, right, then you wouldn't be able to do so. Yeah, so that's the idea of it. So for example, if let's say I give an example if let's say I try to add on one more point here, then which means this graph will not be a bipartite anymore. Why is that so? Because if I try to add on one point and then one edge here, then you will realize that for this new vertex, what is the color that I should put? I cannot put yellow, am I right? Because yellow, then which means that you are connect the same color vertex by one edge already. So you cannot put yellow. Then can I put blue? I also cannot, because in this case, I will have blue. So that's why in this case, it's not a bipartite graph. Okay, so I hope that you have a brief idea on that. So now what can we do is we try to redraw this so that it looks like a clearer bipartite graph. So we can group them into two groups. So in this case, it's either you want to do it vertically or horizontally, it's depending on you. So in this case, then I will have A, C, and E. So A, okay, and then C and E. So this is like one group. Then you can try to put here group one. Okay, because they are under the same color, so which means they are the same group. So I hope that it makes sense for you, because the idea is that between ACE, they cannot connect to each other. So that's why you must make sure that there's no edges connecting them directly. So that's why you can put them into distinct group, right? So the other group that we have is BDF. So maybe you just try to put it like this: B, D, and then F. Okay, so this will be our group 2. So now let's connect the vertices together. So let's look at A. So A is adjacent to F and also D. So let's connect it. So D and also F. Okay, sorry, make sure that you are using your ruler, yeah, so I can't draw like perfect straight line here. Then after that, we have the next one. C is adjacent to all B, F, and also D. So B, F, and also D. Oh, sorry, I draw D first. Yeah, so BDF lah, so all three. Okay, and the last one, let's look at E. So E is adjacent to F and also D. So F and also D. Okay, so after you draw it, then you'll be able to check it with the blue color one again. So it's F adjacent to A, C, and E. So F, A, C, and E. That's correct. So C is B and D. So, oh, sorry. We should be looking at blue color, right? So D is all C, A, E. So D, C, A, E. That's correct. And B only adjacent to C. So B is only directly connected to C. Okay. So which means this is a correct graph. But when you try to look at these two graphs, right, then basically this one gives you a clearer idea that this is a bipartite graph, because you can see that the graph, the vertices that you have is grouped into two distinct groups, and there's no edges that connecting the vertices under the same group. Okay, so this is like identify whether it is bipartite or not, and you try to redraw it, okay, by using the technique of vertex coloring. Okay, so now let's move on to the next one. Okay, the next graph that we have is called as the subgraph. So subgraph is a graph that is a part of another graph with no new edges or new vertices added. So for example, this is an original graph, right? So how do we draw the subgraph of this graph? So you can take anywhere that you like. For example, if I only take out the square part, okay, so make sure that every time when you are drawing a graph, right, you should indicate your your vertices by using a dot, right? So don't assume that people know that the place where your edges intersect is a vertex, because it's not necessary like that. For example, the previous one, you see there is no vertex here, so you cannot assume that the place that two edge intersect is having a vertex. So that's the idea. You must make sure that you draw a round dot. Okay, so in this case, then which means that I can always take out the part for J, K, M, L. So you see, this square is part of this graph without adding any new edge or vertices. Am I right? So this is like one of the subgraph. You doesn't need to include every point, as long as what you are drawing here is one part of this graph. For example, I can also do something like this. Yeah, okay, and this is my J, this is my K, and this is my M, and this is my L. So this is like one of the subgraph for this graph as well. Okay, so even when I move on, I can even like only draw the triangle. So which means like this, like this. Okay, then this is my LKM. So this is one of the subgraph of this original graph also. So even I only try to draw a straight line like this is also considered a subgraph for the original graph. Okay, so that's the idea of it. So something that they might ask you to do is identify whether the subgraph is, I mean, the graph is a subgraph of the original graph or not, or they'll just ask you to like draw and see whether you understand what is that meant by a subgraph lah. So you can draw anything as you like. So even like you want to draw like the triangle over this side also can. Then you try to do something like this. Yeah, this is like consider one of the subgraph also. Okay, so you can see this is N, M, K, L. So the ultimate idea is make sure that you cannot add any new edge or vertices lah. So subgraph is just basically part of another graph without adding any new edge or vertices. Okay, all right, so let's move on to the next one. Okay, so we have come to the last two graph here. So the first one is called as the directed graph. So a directed graph, I hope that you still be able to recall this word. So this is the word that we mentioned in the simple graph just now. So I mentioned just now a simple graph must not be directed or weighted. So this is the directed that I meant. Okay, so later we'll go back to that. So a directed graph, or sometimes it's called as digraph. So it is a graph that contains edges that are directed, and these edges that are directed is called as arcs. So which means that when you have all these lines without the direction is called as edges. When you have this direction, then it's called as arcs. Okay, so the arcs are used to indicate the direction. So for example, you can see it as what we have here. Okay, so what is the difference between having the arrow and without having so-called the arrow? So the idea is, when we try to talk about a simple graph, right? For example, when we try to look at this graph here, so if there is no direction for the graph, then which means that you are able to go from J to K or from K to J, they means the same thing. So in this case, then which means that J can go to N and then N can go to J as well. So which means the one that without arrow is actually meaning that it's like a two-way thing. But for directed graph, right, it's only like one way. So meaning that it will be following the direction or the arrow that you are assigning for the vertices. So that's why when you try to look at this, then you have the arrow to the right. So which means that for these edges here, is going to be from A to B only. There's no B to A. So that's the idea. So this idea is very important when we move on to like the application stuff where you need to know like I mean when we try to talk about like some traffic, so you cannot expect everything will have like two ways. So maybe some of the routes will be like one way, or something that you can try to say is if this network represent like maybe A likes B, then but B doesn't like A. So the idea is that like this is a direction that to show you that it's A like B, B likes E, then all B, C, D likes E. So that's the idea of what the direction is telling you. So it's not like a two-way thing, but it's like a one-way thing. So a directed graph with no loop and multiple edges, for example, this one is called as a simple directed graph. So which means that I hope that you will be able to relate it to what we say in the first type of graph. So if we only mention simple graph, right, then which means it is simple in the terms where you cannot have direction. If you have direction and you have no loop and multiple edges, you can call it as simple directed graph. But it's not a simple graph because this is directed. Okay? Then the last one that we have here is called as the weighted graph. Okay, weighted graph. So this is one of the graph that is very important in application as well. So for this graph, right, each of the edge will be labeled with a number, or in this case, we just call it as a weight. Okay, a number that you can try to see here, like for example, 180, 113. So all these are known as the number or the weight. Okay, so this weight is used to represent some quantity associated to the age. So it's not necessary always to be the distance. Sometimes the quantities can even be the cost, okay? Or you can say things like distance, okay? Or even time also can. So for example, when you try to travel from A to B, how long is the time that you need? Or for you to complete H, then you want to move on to B, then how many minutes you need? So stuff like that. So a weighted graph with no loop and multiple edges will be called as simple weighted graph. So that's why I hope that these two sentences give you an idea what do I mention that simple graph is not directed and is not weighted. Because if let's say it's a simple graph that is directed, it will be called as simple directed. If that's simple and is weighted, then it will be called as simple weighted. Okay, so that's the idea of it. Okay, so now we'll be looking at the very last example just to identify the type of the graph for this four graph, and basically that's pretty much for the lesson. Okay, so let's look at the last example here. Okay, example 4, define each of the following graph as either simple, connected, complete, bipartite, or a combination of this. Okay, so for a graph, it can be, simple and connected and complete, if you get what I mean. Okay, so let's look at part A. So you can see this is the graph. So I guess it's quite obvious that it's a simple graph because there's no loop, there's no multiple edges, and there's no direction, and there's no weight. Okay, so it's a simple graph. So all the vertices are reachable from the other vertex, so that's why it's a connected graph as well. And then is every vertex adjacent to the other? Yes, right? Like for example, when you try to look at this vertex and it is adjacent to the other two, when you try to look at this vertex, it's adjacent to the other two as well. So that's why this is a complete graph also. Okay, so is it a bipartite? So you need to check out, will you be able to use different color to label it? So for example, if I try to label a purple color here, then you'll realize that for these two, I'll need to use the same color. So if they are the same color, then which means that you have one edge connect the same color vertex. So that's why it's not a bipartite. Okay, so now move on for B. So you can see that this is multiple edges, so that's why it's not a simple graph anymore. So is it connected? Yeah, right. There's no isolated vertex, or there's no graph that is separated from each other. So you'll be able to reach all the other vertex by using any vertex here. So that's why it's a connected graph. Okay, so for a complete graph, you must make sure that a complete graph, the basic is that it must be a simple graph, then only you can say whether it's complete or not. So since it's not a simple graph, so it cannot be a complete graph as well. Okay, so now let's look at bipartite. Okay, so let's try out to different color. So if I use brown color, so which means that this one cannot use, this one and this one cannot use the same color, so maybe this one can. Okay, so in this case, then which means that the other one is all adjacent already, then let's try to check. So for this one, I need to use the other color. So yeah, that's correct. They are having different color. Then here, okay, that's good also. They're having different color. But for this one, if I try to make it to, no matter I try to put it as brown color or green color, it's going to be connected to another one which is having the same color. So that's why this is not a bipartite. Okay, so for C, this is quite obvious that it's a bipartite because you can see that this is like one group here, this is one group here, and there is no edges that connected the vertex under the same group, right? So yeah, let's start with the first one first, sorry. So the first one is it a simple graph? Yeah, there's no multiple edges, there's no loop, and there's no direction, no weight. So it's a simple graph. Is it a connected one? Yeah, there's no isolated part, right? There's no disconnected part, so that's why it's a connected graph as well. Is it complete? No, because it's like a bipartite, but then it may be a complete bipartite, but it's definitely not a complete, because if you want it to be complete, then in this case you must connect them as well. So let's move on to the bipartite first. So I guess it's a bipartite, so I hope that you can see that. So when I try to label this with one color, then I'll be able to label the other one with another color. So you can see that all the edges only connect the different color vertex. You do not have any edges that connect the same color vertex together. So that's why in this case, it's a bipartite graph. Okay, so additional, we can try to check, is it a complete bipartite? Yeah, I guess it is. So when you try to look at every vertex, right, it's adjacent to every vertex in the other group. Okay, so 1, 2, 3, 1, 2, 3, 1, 2, 3. So that's why it's like a complete, but it's a complete bipartite. It's not a complete graph, but it's a complete bipartite. Okay, so let's look at the last one. Yeah, so no loop, no multiple edges, no direction, no weight. So that's why it's a simple graph also. Is it connected? No, right? So obviously you have one part of graph like this, another part of it like this. So the vertex here cannot reach the vertex here. So that's why it's disconnected. Then the next one, if let's say it's not connected, then I mean we don't need to discuss about complete anymore. So is it bipartite? I don't think so. So yeah, let's try to do that. As long as you have three, then I don't think I think you can do that. So one, maybe we try to do like this. Oh yeah, this one can. Okay, 1, 2, 3. All right, so you can try to see whether we can draw it or not. So for example, this is 1, 2, 3, 1, 2, 3. So the line that you will have 1, 2. Okay, so if let's say this is the 1, 2, then you have something like this, then the other one goes like this. Yeah, so this is considered a bipartite graph as well, although it's like quite rare one. Okay, yeah, so this is a bipartite graph. Okay, so that's basically all the content for today's lesson. So the main idea that I hope you can try to do within this lesson is to understand every term of it, understand every new vocabulary for you. So make sure that you are using right terminology for every case that you will be doing. So all the question in your textbook, it will be like much more on the common sense application. So just try to understand and see whether you can apply or not. Okay, so that's basically the lesson for today. So see you next week. Thank you.